All right, so good afternoon. My name is Ryan Holger. I'm with Temperature Equipment Corporation. We do webinars here every single Monday. This week's webinar topic is radiant heating and snowmelt systems. So kind of the idea here with most of these webinars is to give folks an entry-level view to some of these technologies and then get you set up in full day training classes if it's something that's very interesting to you. So today's topic will be radiant heating. We'll also talk a little bit about snowmelt and a little bit about radiant cooling as we go along through here. If you have any questions as we're going, please type them down in the bottom right-hand corner in the question box, and I'll do my best to answer them as we go. I'll check them every 10-15 minutes or so. We'll see if we can get them all answered up. All right, so the first thing I just wanted to let you all know, in case you were not already aware, is that there is a 3-day Radiant seminar class this week. It's in Willowbrook, Illinois. It's the 26th through 28th, and today is the 24th, so that's so that would be Wednesday through Friday of this week in Willowbrook. If you didn't get the information on this, let me know. Send me an email, and I'll send you the link to the class. But the Chicago version of that class is this week here. So it's just kind of interesting timing that we got a webinar at the same time. So a lot of the stuff that we're talking about today will lead into that, that full 3-day class. Obviously, in a 45-minute webinar, we can't cover everything we'd like to. One of the things I do want to point out for you guys on the hydronic side of the equation related to these systems is that the minimum boiler efficiency standards just changed a couple weeks ago. I mean, technically they changed 5 years ago, but they just gone live 2 weeks ago. 3 weeks ago, I guess. So effective September 1st of this year, all boilers need to be 82% minimum AFUE. That's the least efficient boiler that you could get. If you have one in stock or we have one in stock, you can still install it, but they can't be manufactured any less efficient than that going forward. Along with that change was the elimination of standing pilots, which most of these systems have already done anyway. And then interestingly is a requirement now that from the boiler standpoint, that you have a way to automatically adjust the water temperature set point. And for most of us and most of our systems, that's going to mean outdoor air reset control that you'll have to do by law on these systems. So all that stuff's going to play into to radiant heating as we go along. And in about 2017 or so, you're going to see 90% as the minimum boiler efficiency. But that's still 5 years away, so you still got time on that one. But right now, it's 82% is the minimum for hot water. So a lot of customers, especially residential, we're talking about residential and commercial aspects of radiant today, but right now we're looking at some residential stuff here. A lot of consumers are interested in green technologies, as you might guess, but it means different things to different folks. So this is just off of a particular survey, this data here. A lot of people are looking to buy green products, and this number goes up increasingly, but how many of them are looking to pay for them is usually a different type of number. So you can see here, basically half of the population would say, yeah, I'd like to have a green product, but only about 20% of them are probably willing to actually pay more to get that green product. So a lot of times to get folks to do something a little bit unique, you also have to show them the energy savings they're going to have. So not just being green, but how much energy can I save in the process. And then in terms of radiant heating, just like with modulating gas furnaces and things like that, like we talked about last week, radiant heating is often sold, almost primarily sold on the comfort benefit in the residential sector anyway. It obviously is a bigger purchase install than a furnace system, so buying a boiler plant and putting radiant tubing in your flooring is going to cost you more money than putting a furnace in. So folks usually do this for the comfort level. We're going to focus on that quite a bit. Commercially, it's typically done for applications where air systems are not very appropriate for various reasons, not so much a comfort thing. But radiant floor systems offer a very consistent temperature versus even the best furnace on the market. Not that I'm bad-mouthing furnaces, obviously. We sell a lot of furnaces here. But radiant floors, the mass of the floor, especially when you put the radiant tubing in concrete, keeps a consistent heat being dispersed to the occupants continuously versus a furnace that's cycling on and off all day long, and you're getting 120-degree air coming out of the diffuser, then you're getting 70, then 120, then 70. So radiant flooring doesn't have that kind of issue. And even though the boiler may modulate, the floor temperature in the space is not going to fluctuate at all. It's going to be within tenths of a degree all day long. So it's very consistent temperature and comfort. The temperatures from room to room are also very consistent. Radiant heating is based on the floor shining on you, as we're going to talk about here in a minute, not so much the air temperature. but we're able to keep one room to the other very consistent. And within the room, it's very consistent as well. You don't have, as the cold issue as you get to the perimeter walls, and then warmer on the interior, or how close are you sitting to the diffuser. Radiant floor heating is dispersed rather evenly throughout the whole space. And you don't have any draft issues as you would have with a forced air system. No need for slippers, right? So you can see some of these things I'm just popping up on the screen here. These are all benefits of a radiant system. There's less issues with dust being circulated, air. Noise issues are almost eliminated completely unless you're sitting next to the room that has the actual boiler in it. But you don't have any noise issues in the space itself. You can put furniture wherever you want. You're not going to block one of the grills. You're not going to block any radiators, things like that. So the basic premise of the radiant system is get the entire system where the consumer cannot see it at all, give them very even temperature and comfort so they don't know that there's anything going on in the background, and make it as quiet as possible. Those are kind of all the goals of these types of systems. So no fans except for the blower motor on the condensing boiler itself, which hopefully is down in your basement where you won't even notice it. Even temperatures from floor to ceiling, from north to south, east to west, that kind of thing. So this gives you an idea, and some of you guys are probably familiar with ASHRAE Standard 55, which is the thermal comfort standard that we use in our industry that dictates the temperature distribution you can have vertically throughout a space. And that's why you see on here 6 inches and 6 feet on this chart. Basically, that ASHRAE standard dictates that between 6 inches off the floor and the occupied zone, which for a standing occupancy would be 6 feet, for a sitting occupancy like a desk or something like that would be 3.5 feet. But in that range there, you're not supposed to have more than 5 degrees temperature stratification difference. So from the floor to basically the ceiling, I need to have this same temperature would be within 5 degrees, which sounds like a wide range, but if you go home tonight and start taking temperatures at your floor and taking at your ceiling, you're going to find 12, 15 degree distribution temperatures between those areas. Keeping it within 5 degrees is very difficult to do with an air side system. You can do it with proper diffuser placement and directional diffusers, but it's a lot easier to do it with chilled beams or radiant cooling or radiant heating panels or radiant floors like we're talking about today. If you keep that temperature within 5 degrees from the people's feet to their head, basically, they don't notice the temperature difference at all. However, if you have stratification, you might have, say, where the thermostat's located on the wall at 4 feet, it's 72 degrees. The stat's happy as can be, but down on the floor, it's 61 degrees, right? And then they'll have cold feet, and they'll feel that problem. That's true both residentially and commercially. So forced air systems don't do a very good job of keeping that stratification under control. As you can imagine, whether we're diffusing air from the floor or the ceiling, it's going to have a bias, right? So if we diffuse it at the ceiling, especially if it's very hot air that we're diffusing above, say, 90 degrees, which most commercial buildings do, that air will have a tendency to stay up at the ceiling, and you're going to end up with very high temperatures up there versus very cold temperatures at the floor. Like this chart is showing you here, you might have whatever 73, 74 degrees up by someone's head, and then down at the floor you may have 55, 58 degrees. But the thermostat, he's right in the middle, and in this particular case, the thermostat's at 68 degrees and perfectly happy. Right? The thermostat is always going to be happy in every system. How good it is above and below that, to the left and to the right of that thermostat, that's debatable. But the thermostat's going to get what he wants because he's the only one getting a vote. Whereas a radiant floor system, we're not really trying to heat the air at all. Heating the air is kind of just an accidental byproduct of heating the objects. The objects meaning mainly the people, but also the furniture, desks, and things like that. Because with a radiant system, I'm not trying to heat air in the space and then the air is around your body and makes you feel warm. I'm trying to directly heat you. So it's kind of like the sunshine, right? Infrared heat. The sun is shining down on me when I'm outside on a 60-degree day. If the sun's shining, I feel pretty good, feel pretty warm. However, if the sun goes away and it's 60 degrees outside, I feel kind of cold. 60 degrees either way. Either way, a temperature sensor outside says 60 degrees, and I'm either feeling comfortable or not comfortable based on the radiant heat shining from the sun to my body. The radiant floor works the exact same way. The radiant floor is literally shining on the occupants with infrared heat, and they're feeling warm because of that, which means that the air temperature in the space can actually end up being lower, and they're still going to feel comfortable. But the air temperatures, because we're not heating the air directly, are very even. So this chart's here showing you a radiant floor system from 6 feet to 6 inches being a fairly consistent temperature up and down. So instead of just heating basically from the thermostat to the ceiling like we do in many commercial buildings and even residential buildings, we're heating the entire person and every object around them. So as the radiant floor shines on me, I warm up. As it shines on the walls or the desks or things like that, they warm up and then they begin re-radiating back towards my body. So those are all helping to keep me comfortable. The other thing is by not having very much air movement in the space, I'm able to reduce drafts. And in the heating season, that's very beneficial because having air move across your body takes heat away from your body, which makes you feel cooler. If you don't have any air, you don't feel that. In commercial buildings, you're still going to have a little bit of air because you have ventilation codes to satisfy, but you'll have much less air than you would in a forced air system when you have a radiant system. Just looking here to see if we had any questions pop up thus far, and we do not, so we'll just continue on for right now. Got to click on that. All right, there we go. All right, so this chart here is showing you the optimal temperatures, and once again, this data is coming from ASHRAE Standard 55 primarily. ASHRAE Standard 55 dictates numerous comfort values to the designer of the system. It's not just a temperature thing. So air temperature is one of the things that's in that standard. The radiant temperature, the mean radiant temperature, the average radiant temperature, if you will, is also dictated by that standard, as are high-end humidity limits, airflow, clothing levels, things like that all factor into an individual's comfort. Some of those things we don't control with our HVAC system, like we can't tell you what to wear, right? That makes it a little bit harder. But we can control the air temperature, and we can certainly control the radiant temperature with a system like this. So this is kind of showing you that this pink zone, if you plotted those values out, this pink zone in the middle here is showing you what the optimal scenario would be, the optimal comfort zone for the average occupant. The data on the left-hand side here is what we can typically affect with a air side heating system, right? I can change the air temperature in this chart's example from anywhere from 40 to 90 degrees, although I'm typically going to be in the mid-60s to mid-70s, so I'm going to be kind of, I think you guys can see my mouse, I'm going to kind of be right, actually we got a little, see if we can do this little pen deal here. So you're going to kind of be, you know, in this range here with your typical forced air heating system, you're going to be controlling that there. Whereas a radiant system, I have very little control, at least directly, over the air temperature. I'm controlling the radiant temperature in the space. So I'm having control over things below this black line over here. And I'm still going to have the air temperature be fairly warmer, but I'm probably going to have it a little bit cooler. I'm probably going to be operating primarily in this range, right? So a little bit cooler air temperature, but I have control over what's going on radiant-wise. It's a lot easier for me to hit space in this pink box, this comfort zone, if you will, when I'm working on the radiant half of this curve, versus if I'm just in the forced air side, the air temperature only side, I got this little tiny band here that I can get. And my furnace may be able to help me get kind of in this range here, but he's not going to do much good other than that range. I got a bigger window to hit when I go to a radiant type system. And you can also see that with a radiant system. Get rid of this pen here. With a radiant system, I am going to have a lower air temperature, right? So in this example here, I'm in the upper 60s versus an air side system, I'm probably in the lower 70s. Anything I can get in this pink box is basically going to be equal comfort to the occupant. So I can have a lower air temperature and be equally comfortable to a warmer air temperature with an air heating system. So hopefully that makes sense to you guys. All right, so that's kind of what this is saying here. A higher radiant temperature in the space reduces the radiant heat loss from the person to the objects. So the way radiant energy works is that the hotter object is shining. I'm saying shining, it's not really a light, but it's kind of like that. The hotter object is shining the energy to the cooler object, right? So the sun is shining energy down to the earth, right? If you're sitting by a campfire, the campfire is shining energy onto your chest, right? But your back is freezing because there's nothing back there at all, but your chest is getting all that warmth from the fire, right? Well, in a normal space, typically the human body, which has, 98-degree internal temperature, 91, 92-degree skin surface temperature, so that 92-degree skin is shining on all the objects. Your chair, your couch, your desk, your floor, those things are all between 55 and 75 degrees in the wintertime. Your body is shining energy onto those things. So when you walk past a cold window, you literally feel cold because your heat is being sucked from your body to that cold window. But when I have a radiant system, the difference is that if I keep all the surfaces warmer than my human body, then those surfaces are now shining their energy to me. So if my floor is no longer 65 degrees cool, and instead that floor is 95 degrees warm, and my skin is 91, 92, that floor is transferring energy to me instead of me getting my energy sucked away from me. So that's kind of the premise of a radiant system, is that the radiant floor or the radiator panel or the ceiling or whatever it's going to be is shining energy to me in the wintertime because he is slightly warmer than my skin temperature is going to be. Versus normal spaces, I'm giving up my heat to all the objects all day long, and I'm relying on the air temperature to heat me back up or at least keep me neutral. The radiant floor will keep me warm instead of me keeping the floor warm. So like we said, because of that, it's very common to see folks that have radiant heating in their building or in their home keep a lower thermostat temperature than they otherwise would. We do a lot of classes here in the office for contractors and engineers, and we always poll people when we talk about radiant systems, see who has a radiant system in their house and what they keep their stat at. And it seems like most folks here in the Chicago area, contractors and so forth, that have something in their own house typically have their thermostat set between 64 and 66 degrees with a radiant floor system. The highest I have seen is 69. The lowest was 62 by polling these people in the class. But usually it's 64 degrees or so is what most folks have it set for. Whereas when I ask the guys that have furnaces in their houses what they keep the stat set for, the range is usually between 70 and 75 degrees. And once again, the worst I've heard is 67, I should say the lowest, and the highest I heard is 77. But usually it's around 72, 74 for the air side system. So usually, I mean, this is showing you 4 on this chart here, or on this description, but usually it's going to be 6, 8 degrees lower temperature that the radiant floor user is going to set on his thermostat than the air side heating user is going to set. And obviously the lower temperature thermostat is going to reduce energy savings. The lower the air temperature inside the space, the less the space is giving to the outdoors. The rate of heat transfer from inside the building to outside the building is based on the delta temperature between those two. So the closer the indoor temperature is to the cold outdoor temperature, the less heat transfers through the wall. So if I keep your space at 65 instead of at 75, I'm going to give less heat up to the outdoors, which means I need to run my boiler less, which is going to end up saving you money. So that's kind of what we were just talking about there. The warmer floor is going to give you better comfort, which is going to keep your thermostat temperature lower, which is going to help you save some energy. There are some benefits to not using ductwork systems in terms of stirring up dust and things like that, but most folks are still going to have a ducting system for cooling and things like that anyway, or a commercial building, you're still going to have it for ventilation in the wintertime. So that's not as big of a deal as you might think it might be. All right, so in terms of laying some of these systems out, and like I said, we have a full 3-day design class coming up this week, Wednesday, Thursday, Friday in Willowbrook. If you need a link to that, if you guys logged in late here today and you want the link to that training class, let me know and I will email you the link so that way you guys can register for that class. But just to give you some kind of rough numbers, just things to think about. On average, we're typically going to have heating circuits limited to about 250, maybe 300 feet per circuit of pipe. The idea with having smaller circuits is that I don't need as much pumping horsepower to push water through these circuits. So we tend to have the circuits be smaller, and we tend to group them by zone, obviously, so we can have individual thermostatic control over each individual zone. So if I got 250 feet per circuit, that's going to cover a certain floor area. That's going to be a bedroom or two or something like that. So every room can end up having its own thermostat for not too much additional cost. It's basically the cost of an extra thermostat and an extra valve versus, on an airside system, I'm going to have some kind of logic control panel, dampers, actuators, and then obviously all the sensors as well. It's pretty easy to zone on a radiant side system, especially if I think about it in advance when I'm laying the tubing out. In terms of thermostats on these systems, this is the one and only time on a radiant floor system that we do not recommend programmable thermostats. Most of you guys probably know me for several years. I've been here 15 years. All that time, being involved with thermostats directly at our company, and I've been a big proponent of programmable thermostats and DDC systems and things like that. However, with a radiant floor system, a non-programmable thermostat is what I would recommend to you because a programmable thermostat never gets a chance to do anything. The reason being, these floors have a very large thermal mass, especially when you put them in concrete. The picture down there is showing you one that's laid with panels and wood, and then there'll be a subfloor over the top of that. But when you put it in concrete, it ends up being a very large mass. It takes a very long time to heat that mass up. It takes hours to heat it up, sometimes even a full day. And the same thing to cool it down again. Here in the lab, here in Melrose Park, in our training lab, we have a very small radiant floor system. It's probably 5 foot by 7 foot or something like that, concrete, and it can be fed off any one of our boilers in the lab, including a 140,000 BTU Munchkin boiler. And when I turn that thing on for a radiant class, I got to do it 3 hours in advance just to get that concrete floor warmed up. And that's with a very large boiler being fed into a very small radiant floor. So you can imagine how long it takes to heat up an entire house. So the good news about that is that once I get the floor warm, it doesn't take a lot of energy anymore. That first day, yeah, I run my boiler nonstop all day and get the floor warm. But then once it's warm, all I'm doing is maintaining the heat of that floor. I don't want to put the thermostat into a setback mode, because if it goes into setback mode and says I don't want 70 degrees in the space anymore, I want 65 degrees in the space, it's going to take me 3-4 hours with that floor being off to cool the air in that space down. Because remember, the thermostat is sensing air temperature, not really floor temperature. Although there are some fancy stats out there that can get a floor sensor and try to bias that, but those generally don't work out as well as you might expect. So the regular thermostat only senses air temperature. He can't react at the slow speed of this floor. So he ends up taking too long to cool down and wasting energy, and ends up taking too long to heat up in the morning, and which causes comfort dissatisfaction from the occupants. So with the radiant floor system, the recommendation would be a non-programmable thermostat. Now, in the picture down here where we have the wood panel system as opposed to a concrete mass system, there might be some benefit to then using a programmable stat, because it's not going to take 8 hours to warm the space up and cool it down. It may only take an hour or something like that. So you might want to consider having a programmable stat with those systems. You can always turn the programmable feature off and not use it. But with a concrete system, don't even waste your money. So we can put this radiant tubing pretty much anywhere. The best place to put it, especially for new construction, is in concrete. Ideally, you can do that in the basement floors or the slab floor on a commercial building. That's very easy to do. If you want to put it in as a retrofit, we do what we call staple-up systems very often, where we'll go underneath the wood floor in, say, your kitchen or your bathroom, and staple the tubing to the floor there, and then put insulation underneath that with aluminum foil facing to keep the energy deflected upward. Those work best when you get the tubing very close to the floor surface area. You don't want to have 3-4 layers of wood in between there, or carpeting or something like that that's going to act as an insulator. So those staple-up systems really only work for floor tempering of tile or wood floor areas. So we do those often in bathrooms or in kitchens. If you really want to heat your house with it, you need to put it in the concrete, or you need to rip up your floor in your kitchen and those other areas and put in some kind of paneling system like this one here that'll spread out the heat with those aluminum panels. You can use the radiant heating system as your only, or as your primary heating system, if you will. Those work best with the concrete systems. If you're going to do it on the wood, you're probably just going to be warming it, and then you're still going to have a heat pump or a furnace or something like that to supplement it, or maybe some radiators with off the same boiler kind of thing. Sometimes we'll call that a hybrid system, where we'll have radiant floors tempering spaces that have cold floors, cold wood and tile floors, but then we'll also have some kick space radiators and things like that in other parts of the house by the perimeter. Concrete, you don't have to worry about it. You'll be able to heat the whole house with the concrete. Once you do decide to go to a radiant floor system and you purchase a boiler, then it makes sense to use that boiler to heat lots of other stuff in your house. So like I said, you might have radiators in some older parts of the house. Maybe you put an addition on, put floor tubing in the new addition, but it's easier to go back and retrofit radiators in the old area as opposed to floor tubing. You can use that same boiler to do snow and ice melt, which we'll talk about in a little bit, to clear out driveways, sidewalks, and things like that. You can use it to heat your swimming pool. You can use it with an indirect tank to heat your domestic water. I mean, once you got a boiler there and you got the burner going, you might as well put heat into every spot you can off of that one burner, as opposed to using a 50% efficient water heater. You already got a 95% efficient boiler sitting there. Let's just look real quick and see if any questions had popped up recently. And it looks like we're good on the question front here. All right, so radiant systems, they're hydronic systems, obviously, but they need cooler water temperature than many other hydronic systems. So the typical hydronic system is designed for 180-degree supply water being delivered out to a bunch of radiators with a 20-degree delta T. Well, if I send 180-degree supply water to the floor of your kitchen or your living room or your office or wherever it is, that's going to be a lot of heat at your feet, and that heat is going to basically make you dance on the floor. It's going to be too hot for you to stand there, and it's going to be very uncomfortable. So we have to use much lower water temperatures. Radiant systems, we're typically supplying water from the boiler in the range of, so let's say, 85 to 110 degrees. The design is going to be somewhere in that range, 110 being kind of the maximum, maybe 115 as an absolute maximum. So you're going to have these lower temperatures. So these radiant systems lend themselves very well to condensing boilers. For you guys that are familiar with boilers, non-condensing boilers, right? It's not that there's some kind of special magic boiler that allows them condense or non-condense. It's just that the materials that they're made out of can tolerate the condensate. So a non-condensing boiler would be a cast iron or steel boiler or a copper boiler. And if I allow those boilers to have lower temperatures, it'll cause condensation, and that condensation will eat a hole in those ferrous metal heat exchangers. A condensing boiler, by contrast, will have a stainless steel heat exchanger or titanium or copper nickel or something like that, aluminum, that could handle, and non-ferrous metal that can handle that condensate. So condensing boilers can handle lower return water temperatures and enjoy the extra energy benefits of that condensate. So they lend themselves very well to radiant systems. So we haven't done a radiant system in our building, in our office here, for probably at least 12 years that didn't have a condensing boiler on it. The old, cast iron boilers with a mixing valve and all that, that's all gone these days. Everybody who does radiant would use a condensing boiler as opposed to a non-condensing boiler, because we can set the water temperature for whatever we want, tell it to give us 95-degree water or something like that, and it works perfectly well. Additionally, if you have a 95% AFUE rated boiler, that's what he is at his design conditions, which are probably, whatever, 140-degree return water or something like that, or 160. If I run that with lower water temperature, the efficiency actually goes up. So many times you'll have a 95% condensing boiler that's actually behaving like a 99% condensing boiler when you slap it onto a radiant system. So you do even get a higher boiler efficiency because of the lower water temperature. So not only do you save energy because you've changed the space temperature set point in your space, but you also save energy because you're operating the boiler in a condensing mode more frequently, which helps you out as well. You could also certainly use an electric boiler, although here in the Midwest, natural gas is pretty cheap, so an electric boiler doesn't make a huge amount of sense, although it may be better than propane for some customers depending on your propane cost. You could couple these radiant floor systems to ground source heat pumps, which is a fantastic energy saver, obviously. It's hard to put a regular heating system, hydronic heating system on a ground source heat pump because you can't get the 160 or 180 degree water. But those water-to-water ground source heat pumps can very easily produce 115, 120, 125 degree water, so they're very well suited to use with a radiant heating system. And you can also tie them to any other type of radiant source as long as you have mixing control devices to keep the water temperature from getting too hot. Solar panels have become popular lately to use for both domestic water as well as radiant heating systems, and you can also tie them into other renewable-like sources such as a wood-fired boiler or a corn-fed boiler or something like that. Just keep in mind that the water temperature needs to be very low compared to a traditional system. So if you have a hot heating device like a full cast iron boiler or a wood-fired boiler, you'll have to have mixing valves. All right, so we already mentioned this. The lower delta T from inside to outside is one of the energy savers. The decrease in space temperature set point saves energy. Modulating boilers help save a little bit of energy. The cold return water temperature on a condensing boiler helps save a little bit more energy. And the lower we can put the thermostat, basically the more energy we can save in the space. So setting it 3 degrees lower, on average, saves about 1% in the fuel consumption. So if I can get your set point to be 6, 7, 8 degrees lower, there's going to be 2-3% energy savings right there off the top. The other thing we might want to mention, other than the gas saving discussion we had just a minute ago, is on the electrical side of the equation, is that pumping water in almost every single scenario is much less expensive than blowing air with a fan, regardless of how efficient your fan is and how great of an ECM motor you have. And then you could say, well, I have these, very fancy variable speed ECM residential fans that are, only costing me whatever, $100 a year to run. Well, the pump guys do the same thing now. They have variable speed ECM controlled pumps that do the same thing. So this is saying here a typical residential circulator may draw 50, 60 watts of power, but if you use one of those ECM ones, you're drawing something like 8, 10, 12 watts. So it's the same kind of concept you can do there, but the pump is always going to be a better way to move energy than a fan for both residential and commercial. So you can save quite a bit on the electrical side of the equation as well. Real quick, I just wanted to touch on some of the rebates that are involved with these boilers before we continue on with snowmelt discussions and things like that. I'll show you some residential and commercial rebates that tie into these boiler systems. So specifically for right now, for Nicor, we'll hit the other utilities in a second. Nicor has 2 residential rebates available for boilers. It's 90 and 95% of the 2 tiers, and that corresponds to $350 and $450 rebates you can get residentially. You do have to have outside air reset controls, which come standard on most condensing boilers anyway, so that's pretty easy to do, and the radiant system will do well with the outside air reset schedule. If it's commercial Nicor, the dollar amounts are a little bit larger. If you get, say a 500,000 BTU boiler like a ModCon 500 that we use here frequently, the rebate for that example would be, down here at the bottom, would be $2,500 for a 90% or more efficient boiler. If you're in the Peoples and North Shore gas territory, you should be aware that as of Friday, they just doubled their rebates. That rebate doubling goes from Friday of last week through the end of November. So basically from now to Thanksgiving, you can get double rebates, which means that for a residential, and this doubling is for both residential and commercial, by the way, but for a traditional residential boiler, it can be 90 or 95% condensing boiler. For Peoples Gas in the city of Chicago, you get $1,000 or $1,200 for the 95%. For North Shore Gas, you get $700 or $900. It's probably the first time you guys are hearing about the double rebate because it just got announced on Friday. So you might as well take advantage of that over the next 2 months here. And by the way, the same doubling applies to furnaces and water heaters and all that stuff. The only thing that didn't double was the attic insulation. All the rest of the residential and commercial prescriptive measures doubled. So $1,200 off a condensing boiler is a pretty good deal. $900 is a pretty good deal too. Commercially, they doubled as well, although I didn't update my chart here yet. I didn't have time to do that. So instead of $4 per MBH for a 90% commercial boiler, you would be getting $8 for each MBH. So a million BTU boiler would be an $8,000 rebate. A ModCon 850 would be a $6,800 rebate. So this chart right here is before the doubling. So it's a little bit better than this chart even. If you're doing a public institution, so you're doing a village hall, a police station, a federal building, something like that, you don't get your rebates from the utility. You get them from the state DCEO department. And in those cases, this is commercial I'm talking about. For a typical smaller condensing boiler under 1 million BTUs, it's got to be 90% efficient, and you get $7 for every 1,000 BTUs. So a 1 million BTU boiler would get you a $7,000 rebate, which is quite substantial. If you're out in Indiana, residentially speaking, the boilers are same tiers as we have in Illinois, 90 and 95%, corresponding to $300 and $450 rebates. And once again, you have to have outside air reset controls to get those rebates, which lends themselves very well to radiant systems. If it's a commercial building with a larger boiler, it's basically tiered on how big the boiler is, but the typical commercial boiler under 1 million BTUs in size, it's 90 cents for every MBH. In terms of boiler size, and all these are based on boiler input sizes. If you're up in Michigan, residentially, 92% boiler gets you a $200 rebate. Commercially, a space heating boiler has to be at least 88%, which would include all the condensing boilers, obviously, plus a few near condensing. You get a $1.50 for every MBH in size of the boiler. Up in Wisconsin, I don't know if you guys are called in from Wisconsin today. The residential rebates are 90 and 95%. So you kind of see the theme here. With the exception of Michigan, almost every utility in the Midwest here uses 90 and 95% as their tiers, and the dollar amounts are just a little bit different for each utility. But for Wisconsin, it's $300 and $400 for 90 and 95%. Then commercially in Wisconsin, the smaller boilers, as you can see here, these modulating hot water boilers got to be 90%, and you get a fixed dollar amount, $200 or $250. Then when you get to the bigger boilers, it's so much per MBH of boiler input, kind of like the other utilities. So a condensing 1 million BTU boiler would be $2 per MBH, so it would be $2,000 rebate, that kind of thing. All right, any questions on that? Let me see. Oops, let me see if any questions popped up there. Got skipped ahead here. Hang on. All right, now we pull the questions up. All right, no questions right now. If you have any questions, guys, type them in the bottom right-hand corner, and I'll do my best to answer them here. All right, so let's look for a little bit at some typical applications that you might be using these type of systems on. Like I said, in residential spaces, either as a retrofit or a newer install on the upper floors, you can put the tubing underneath the tile. You can staple it up if it's a first floor from the basement. If it's a second story, you're obviously going to have to pull the floor up. But you can do that over the underneath the tile. You can also embed it right in the concrete, which is one of the more comfortable ways to do it. It's very easy to do for basements and slab on grade type applications. You can use this to heat your garage. And there you can have the debate a little bit on whether you want to have a glycol in your system or not. In your garage, you should be fine without the glycol unless you unfortunately leave your door wide open on your garage for long hours at a time. Then you might have to be a little concerned about that. But a lot of garages go in without any glycol in the system. Commercial applications, typical applications there, office buildings. Speculative office buildings obviously won't do this kind of thing, but owner-occupied spaces are more likely to do so, especially if it's a longer life facility. Some schools are starting to do this now, especially daycares and things like that, where they have small children playing on the floor all the time. Some warehouses do it because they open up the dock doors all the time. And when you open up the dock doors, all your heated air just gets sucked right out the door. But if you have a radiant-based system, whether it's radiant tubing in the floor or whether it's an infrared heater from above, you're not heating the air. You're heating all the objects. So you're heating the floor, you're heating the ceiling, you're heating the walls, you're heating the racking, you're heating the forklifts, you're heating the people. So warehouses, especially high-volume door warehouses, may choose to use a radiant-based system. One of the very popular ones for commercial is car dealerships and service depots like bus terminals and things like that. I've heard several stories now about technicians leaving one car dealership to go work for another because they have a heated floor. A lot of car dealerships will put infrared heaters in on the ceiling, which is nice. However, the problem with that is the technician is generally under the vehicle, which is not getting any of the heat shining on him. The radiant floors is a much nicer work environment. And I guess if you're in an industry that's in higher demand, like a car dealer technician, maybe that helps you retain the techs that you want. We also do it frequently in like car washes, for example. And there we do it because we don't want to have any ice build up where the water's running out, from right when you meet in the indoor to outdoor portion of the car wash. We don't want to have any ice building up there and cars sliding around, so we will frequently heat car wash spaces with radiant tubing as well. So museums like it because of the reduced airflow in the space. If you're not aware of it, airflow in a museum tends to cause things to break down and depreciate faster, so they want to reduce the amount of air moving in the space as much as possible. Radiant systems obviously help do that. Like I mentioned, daycare facilities already. Tons and tons of colleges put these systems in. They have the longevity foresight to know that they're going to be in this building for the next 50, 60, 80, 100 years. So they'll invest in things that save energy even if the payback isn't going to be for 6, 8, 10 years because they know they're going to be there. Whereas an office building might not do that. Retirement homes, very popular for radiant heating. Those folks are always cold. Radiant heating helps warm their body as opposed to the air around their body, so they tend to feel comfortable. Hospitals are very popular as well. Once again, with the ability to reduce the amount of air moving around, we can filter less. We still have to bring plenty of outside air in for ventilation reasons, but if my ventilation system is only 40% of my otherwise air side system, that's a lot less I have to do on the filtration side, and the filtration levels in hospitals are pretty high, so doing as much as I can with radiant not only saves the energy, but it also reduces how much I have to buy and change filters and things like that. And then prisons are extremely popular for Radiant, and that's because we're very concerned with keeping prisoners happy. No, actually, it is because of that, I suppose. Unhappy prisoners tend to lead to rioting prisoners. But the real reason is if we put airside systems in prisons, or at least larger airside systems, that tends to be something people can tamper with and probably make weapons out of. Whereas you put radiant tubing in a floor, it's kind of hard to get the tubing out of the ground at that point. So it's just less tamper. It's more tamper-proof, if you will. So that's some of those applications. There's just photos here we're showing you of laying some of these tubing systems out. Fire stations very often do radiant flooring. Even if they don't do it on the whole building, they very frequently will do it nowadays in the dock area. Once again, when those fire trucks lift up the dock doors, they fly out of there, they tend to leave those doors up for the next hour while they're on a call or whatever they're doing. And that, if you heated the air in that space, all the energy would get sucked out of there very quickly. If you do radiant heating, you're not heating air, you're heating objects, and it tends to save energy even when the doors are open. So fire stations, bus stations, warehouses all do it for that type of reason. So these are just examples of tubing layouts. And if you're interested in laying out tubing, we do run classes here in Melrose Park, not only on how to size and space the tubing, but also on how to actually install it. So we actually will show you and make you physically in the lab area, install tubing on a ceiling, install it on a floor system, lay it down, tie it off, all that kind of stuff. So we do classes like that. If you're interested in that, let me know, and I'll let you know when the next one's going to be. Anything with dairy, anything with barns for animals, we are very good in radiant applications. Some of you guys get involved with it, some of you don't. There's several studies out there that relate dairy milk production to the temperatures of the animals themselves, and heating it from the floor is a lot better because the barns are typically pretty leaky and often have large openings in them. So heating through radiant systems saves a lot of energy for those spaces and produces better output in terms of milk and things like that. Greenhouses for plant life. I don't know if you ever tried to heat a greenhouse with a unit heater, but it's very challenging to do to heat an all-glass building. So heating it with radiant-based, whether it's infrared or radiant tubing in the floor, is a much better solution. Athletic stadiums, very common as well, especially ones that have natural turf. They will put PEX tubing underneath the turf in order to keep the roots warm so they can continue to grow grass all fall long. I'm pretty sure the Chicago Fire Stadium, the Toyota Park in Bridgeview there, I'm pretty sure they have this type of heating system in their floor. I don't know about Soldier Field. Actually, Soldier Field, I know they do have a system as well, although they tend to have other problems with their turf. So I should have probably made that potshot comment at them. All right, let me check the questions real quick here. All right, looks like we're good on questions. If you have questions, type them in. A couple of comments on a few other systems here. One of which is radiant cooling. So not only can we heat a building by putting warm water through tubing in the flooring or ceilings or walls, we can also cool a building that way, right? So instead of sending 90-degree water through the tubing, we could just send 50-degree water through the tubing, and that would cool the building off. Although if I send 50-degree water through there, chances are pretty good that would be below the dew point many times a year, and that would probably cause condensation, and you obviously don't want to have condensation on your floor. So if you're going to do a radiant cooling system, there's lots of design considerations in regards to controlling dew point. For one, it typically means my radiant cooling water is going to be fairly high, 56, 57, 58, 59 degrees, something like that. So that way I don't go below the dew point. I'll also put controls on this system to make sure that I don't send water around the building that is cooler than the current dew point. But if I do that, I don't have any way to dehumidify the air, right? Because a normal cooling airside system, I am both doing sensible and latent energy. If I have a radiant cooling system, it's sensible only. It cannot do any latent cooling, because if it does, once again, I'll have condensation on the floor, which won't be good. So I still have to have a separate latent system, which usually can be doubled up with my ventilation system. So I'll typically have 100% outside air ventilation air handler that's doing 100% of my space latent load as well. The vast majority of the energy savings on these systems comes from A, the elevated chilled water temperature, which I can get from numerous sources. We can talk about that offline if you guys need to. And B, the reduced fan horsepower, because I don't size my system for my full cooling load anymore. So I don't have a, let's say, for example, 10,000 CFM fan. Instead, I have a 3,000 CFM fan because he's just doing the ventilation load in terms of CFM. So I get a huge fan savings on those type of systems. This is appropriate for some commercial buildings and not others. Obviously, any buildings where you're going to be opening doors and leaving them open for a long time wouldn't be good, like a warehouse, for example, or that car dealership thing we mentioned earlier. So the places that radiant heating thrives tend to be the ones that are, a little bit scarier for radiant cooling, because I don't really want any outside air coming into my space and causing me to hit the dew point. But other places like schools, universities, libraries, things like that, radiant cooling can be done quite nicely. We tend to not recommend it for residential applications, and that's not because we can't do it. It's just because we're worried that the people operating the system won't be able to understand it, and the controls that are put on there won't do a good job of policing it, and we could end up hitting the dew point. So in concept, we can do it. We just haven't done any that way, at least in our office. Although Bill Bailey and I are going to go look at a radiant cooling house next month and kind of check and see how they did that. But right now, we're kind of only recommending it for certain commercial applications. So kind of the idea there is kind of similar to what we do on the heating side on these larger commercial buildings, is we're just trying to take care of the base thermal load of the building, the base thermal cooling load of the building. The latent is still handled by an air handler, and sometimes you might need some additional cooling sources at the perimeter if you have not done a good job with your windows and insulation and things like that. If it's a new building and it's built to current standards, you should be able to cool the entire building with the radiant cooling panels in combination with the ventilation latent air handler. All right, so a couple quick things on radiant design systems. Basically, the way you design a system is the same way you design any other hydronic system, or any system for that matter. The first thing is obviously doing a heat loss for the space. So, what's my load going to be? Whether it's heating or cooling system, I'd be doing the same thing. And then boiling, and then backing from there, from the space out all the way back to the boiler, right? So what's my heat loss going to be? I'll use that to size up my panels or my floor tubing. If I'm going to do that, how much tubing do I need in the floor, and how far should it be spaced based on what the load of that particular space is going to be. That can also determine my pipe size. And backing from there, and once I have all that, so I know my pipe size and the flows and water temperature that I need, I can use that to size my pumps and all the way down the line, just like I would on a regular hydronic system. So nothing's really different there other than the fact that I'm putting tubing in the ground. We do have some cheat sheets that we use for that. Obviously, cheat sheets can get you in trouble. We know that, but we know folks are going to do stuff on their own anyway. So just for example, up on the screen here is one of the cheat sheets that Bill in our office often uses for radiant systems. This is specifically for heating, this chart. We don't have any cheat sheets for cooling because at that point we're in a fairly engineered system. But residentially speaking, if you're putting it in a concrete floor, you could probably expect to get about 40 BTUs per square foot, versus if you're putting it into some kind of lightweight system like wood flooring, or putting it between the joists in a retrofit, you're probably only going to be able to get half of those BTUs out of the system. Commercial, similar kind of thing. We're going to get up to about 40 BTUs. Water temperatures, like I said, you're probably going to have 115, 120 at the absolute max. It's much more common to design things in the 100, 105, 110 degree range. And then you'll use an outside air reset schedule to actually run it between, say, 85 and 110 or something like that. In terms of flows, the kind of general recommendation, if you're going to use half-inch PEX, which is very common. There's obviously larger and smaller sizes than that, but half-inch is one of the more common ones that we'd use. For example, if you had 300 feet of pipe at half-inch PEX, you'd have sizing for 1 GPM for each loop there. Spacing residentially, we're typically doing about a foot apart is the most common recommendation. Commercial, as a rule of thumb, we tend to use a little bit larger pipe than we do residentially. We tend to use 5/8 inch pipe instead of half-inch, and we tend to space it a little bit more. Residentially, we space them a little bit closer, which dictates the smaller pipe. We space them a little bit closer because people are typically walking around barefoot and things like that. So we don't want as much, I guess, how would you say it, as much deviation across the floor with, so putting the tubes closer gives us more even temperatures on the floor. Whereas commercially, you tend to have a thin layer of carpet on there, plus people got socks and shoes on, so you can spread it out a little bit more and still get pretty decent comfort. So this is just page 1 out of 10 pages of Bill's, Bill Bailey's typical cheat sheets at our office here. giving examples of how long it might take to lay the tube and things like that. So if you come to one of our rating classes, we'll obviously be working off these cheat sheets as well as doing actual calculations. And then if anybody wants these cheat sheets now, just send me an email and I will send them over to you. Just gives you an idea of what they are, some of the tables and stuff that are in there. It's nothing overly exciting, but just to give you an idea. We don't have time to go through it in great detail today. All right, so the design process is pretty much the same with the exception of the terminal device, which in this case is a radiant flow with PEX. But the load calcs are the same. The rules on how you size pumps and all that is the same. So we're just doing a little bit differently. Real quick, snow and ice melt systems have become quite popular. These obviously do not save any energy because we're heating the outdoors. However, they don't waste a ton of energy either. As you're going to see when we show a couple quick examples here, the amount of hours we actually operate them, especially in our climate, is fairly minimal. So it's not like we have BTUs going outdoors all day long all the time. We only got to run them when there's actually snow falling. The most common ways we use these are to either avoid shoveling snow in case of residential applications, or in the case of commercial applications, to reduce the chances of slips and things like that, which tend to be lawsuits later down the road. So many commercial facilities will want to do that in order to avoid being sued later, and it's cheaper to run this thing 10 days out of the year than it is to get sued once. And I want to think of it that way maybe. So common to do sidewalks, steps, like if you do steps, especially if they're narrow steps like on an old church or something like that. But sidewalks, steps, residential driveways, handicap ramps, commercially speaking. You could theoretically do an entire road, although that's fairly rare. You could do a bridge even if you wanted to, which is also fairly rare. We do a lot of car washes this way. We do a lot of ramps leading up to parking garages, as well as the handicap ramps. We do helicopter landing pads, sporting arenas, things like that. So kind of the things to kind of think about when you're sizing one of these systems, and Bill at our office is pretty good about this. He's been doing it for 20-some years, so he can help you size the system if you need help with it. But things just to think about are, what's the snowfall in your area? Like how many events do you even have per year? And what's the maximum snowfall based on the weather data going to be, right? What kind of humidities do you deal with in your area? And how urgent is it to melt the snow in this particular facility? Do I have to have it such that snow never accumulates on the ground whatsoever, or can I handle a little bit of accumulation, then kick on the snowmelt system and get going from there? So if it's like a hospital, emergency drive-up, obviously there I'm going to run this snowmelt system almost all the time to avoid any particular snow falling on there and accumulating at all. Whereas at your house, you may be able to flick the switch on once you see it start snowing, kind of thing. So we'll talk a little bit about that. Obviously, we can't design for every scenario. Even the best snowmelt systems didn't do very good a year and a half ago when we had that huge, blizzard-like snowfall. So you can't expect it to do everything. But if you can expect it to take care of most of the days of most of your winters, that's usually what we're targeting here. Most snowfall, the other thing to think about is, when does it actually occur? It's very rare to get snowfall on the coldest days of the year. So when it's -5, 0, even 10 degrees outside, you're probably not going to have any snowfall. It's just too cold for it to actually snow. Most of the snowfall is going to be occurring probably between 20 and I'd say 35 degrees outside. That's when the bulk of your snow hours are going to be. It's just conducive to making snow. It doesn't have to be below 32, by the way. It just has to be below 32 where the snow is made up in the stratosphere, and as long as it's cool enough at the ground level for that snow to continue falling. So we often can start these snow systems at 35, 37, 39 degrees, even though you say, well, it doesn't freeze till 32. We want to get that snow and get rid of it right away. The other reason I mentioned the temperature not having very many snowfall hours when it's below 10 degrees outside is because we typically have to size our boiler plant for a 0 degree or -5 or -10 degree day or whatever your design condition is where you're at. But I don't really have to have it do all the space heating of the building and the snow melt at the same time, because it's probably not going to be able to snow when it's below 0 degrees outside. So I can size my boiler for the building for what his loads are at his design temperatures, and I don't have to upsize him to do the snow melt. I just have to have a heat exchanger sitting over here on the side, so I can send some water over there to the heat exchanger for some moments in time to go melt some snow. There's different classes of snow melt that we'll talk about, but it's basically residential, commercial, and institutional facilities, and it really relates to mainly how we're going to control them as we talk about here. So things kind of work the same. We got to figure out our load first, which is going to come from the snow data. So it's not sized like a building load, but we still have to figure out a load. Once again, those cheat sheets I pulled up a minute ago had some snow melt recommendations for the northern Illinois, southern Wisconsin type area. So you can use those, or you can use your own data if you have that. But once we're able to do that, we can use that to base the size of the tubing that we're going to need, size our pumps based on that same kind of drill we talked about a minute ago. And we'll work that all the way back to our to our boiler plant. So that'll size our pipes, it'll size our circuits, it'll size our pumps, it'll determine our spacing and all that kind of stuff. So control strategy is the one that's going to be a little bit more interesting, how we choose to run it. Like I said, there's technically 3 classes: residential, commercial, institutional, and it really is going to depend on how we decide to control this guy. So the class 1 is what we typically use residentially. It's basically going to take care of 98% of your snowfall issues. Yeah, there's going to be times when there's just a ton of snowfall and it won't be able to keep up, but usually we're not going to design it for that because the system's going to be twice as big as it needs to be, and we don't really want to do that. You can have some accumulation for a little bit of period of time, so it may take a little bit longer to melt the snow off because the system is going to be a little bit smaller. All right, so there's just pictures of, doing driveway melts and things like that. That's actually a good one because this guy did his snow melt all the way up to the road, so you can get out of your garage and down your driveway, but it doesn't really matter if the road's not plowed yet, right? Class 2 systems are what we use for typical commercial spaces. So these are going to typically be like this picture shows here, a parking garage ramp, or in front of a senior center or something like that. These are basically sized to be able to handle 100% of the snowfall. So these are going to be a little bit bigger than those Class 1 systems, a little bit bigger in terms of the boiler and GPM capacities, because we want to be able to take care of all the snowfall days of the year. But we can't have a little bit of accumulation on there. So even though we'll be able to take care of all the snowfall days, it doesn't mean we're going to instantly melt all the snow right away. So we might have a little bit of accumulation on the actual ground as we start to melt it off. So that's just showing examples of that. Just, it says it's commercial. Really, it's just a roadway for a subdivision kind of thing. Sidewalks are a very common application in front of stores, in front of banks, in front of downtown high-rise buildings and stuff like that. There's a parking garage example. Parking garage ramps are very common applications because they're on an incline, so cars tend to slip more on the ice there. So we do a lot of parking garage ramps, both residential new construction ramps as well as commercial parking garage facilities, like for retail spaces and things like that. Just showing you some of those. You can put it under concrete, you can put it under asphalt, you can put it under pavers. There's choices there. Here's a Class 2 system on when they redid some steps at a church. These are obviously narrow steps, so having the snow melt helps there. They couldn't make them much deeper steps because then they extend out into the roadway. So putting snow melt in is one way to help out with that kind of thing. Then the last type would be Class 3 systems, which would be what we use for institutional type facilities. Specifically, the most common examples are going to be emergency room pull-ups for hospitals. They're going to be helicopter pads, things like that, where we are willing to spend the extra money to get the bigger boiler system, willing to spend the extra money to run it more hours of the year in order to make sure that we have absolutely no snow and ice on the ground at all. So we're trying to melt this snow off immediately as it's coming down, and the goal is to really have nothing at all, although technically you could have a little bit of accumulation for a little bit of time. But these will tend to lend themselves to larger boiler plants and more energy consumption. There's a medical pad being poured. All right, so in terms of control options, and these tend to also kind of go with the type of class system that you have. Oops, sorry about that. Let me check real quick if there's any questions here at the moment. Oh, we do have a couple questions. Let's see, both of them are from Robert O'Brien. Let's see if we can answer them here. This is going back to the radiant cooling discussion. If you address the latent cooling load with a DOS unit, which is 100% outside air unit, is infiltration the only reason not to run chilled water in the radiant system below the dew point? Mostly, Robert, with these systems, we need to have a radiant cooling system be installed in a building that has a very good skin, a very good perimeter, where the infiltration is minimal. But infiltration is not really considered directly in the discussion of these systems. We can never actually run the chill water system below the dew point, below the indoor dew point. So no matter how we got to the dew point getting low, whether it's because the DOS unit got shut off, or whether it failed, or whether someone left the window open, or whatever they did to allow the dew point to drop in that space, if it ever does drop, I got to shut off the chilled water, or I got to raise the chilled water temperature to keep it above the dew point. So you have to put the latent cooling DOS unit in to take care of the outdoor ventilation load as well as the latent load of the occupants in the space. But you also need to have safety controls on there, specifically a dew point sensor, to measure if I ever get below the dew point, I need to raise my chilled water temperature to keep it above the dew point by about 2 degrees. So that could be because of infiltration, but hopefully not, because these tend to go in systems that are well insulated and well sealed. But it could be because of infiltration, it could be because that someone propped open a front door in a lobby, it could be because the window's open, it could be because the air handler failed. But whatever reason the dew point was allowed to get out of control, I got to be able to reset the chill water temperature to keep it above the dew point. Robert's second question is, what is the typical water supply temperature for a snowmelt system? The snowmelt system does not need to be very hot. It's not like I need to send 180 degree water out there. Let me see if there's anything on Bill's cheat sheet, but it's very common that you'd have water, 60 degrees or something like that. It doesn't need to be very high. Let's see if he put anything on here for the snowmelt page. Here you go. Here's on the high end, 110, 120, 130 degrees, like a radiant system would be. But as long as it's above 50 degrees, you're probably going to be able to melt snow. So don't look at this cheat sheet here and say that I have to have 120 degree water to melt snow. If you have some other source of free energy, like you have condensate coming off a cooling system in the wintertime, and that condensate is 80 degrees or something like that, or whatever it is, I don't know, maybe off a cooling system. But you could use other sources of energy to do some of that snow melting if you need to. You'll need a higher flow rate. The lower the water temperature, the higher the flow rate you'll need. But for a generic system here on this is the snowmelt cheat sheet Bill has. For a generic system, let's just say 120 degree water temperature might be your design. So let's jump back over here. Wait a minute, that's not the one. Sorry about that. I think I accidentally closed my slide when I switched over. All right, sorry about that. Let me pull it back up real quick. There we go. There's today's slide. Okay. So now we're back to Snowmelt Controls. So the three main choices of controls. The simplest one being is number 3 down here. It's manual system with no temperature control. It's basically a light switch on the wall. You're at your house. You see it start snowing. You turn on the switch, which kicks on your pump, which starts pulling water out of your hydronic loop for your house and sending water out to the heat exchanger for your snowmelt system. The problems with that are if you're not there to turn it on, obviously it's not going to do anything. And once you accumulate 6-7 inches of snow, turning it on is not going to help you much because it's going to melt the snow on the bottom there, and then the cold snow on top is going to re-ice that continuously. So a manual system is generally frowned upon, and we don't install those systems out of our office. The second choice might be a manual initiation. I guess the other problem with number 3 is that once you turn it on, you got to remember to turn it off. And if you forget, and it's 3-4 days later, or you forget all the way until you get your gas bill, you've been heating your driveway for 3 weeks when there's no snow on it, you're going to get pretty pissed off. Number 2 is turning it on manually, right? So you still have to have someone there to turn it on. They got to remember to do it, but it's a timer switch. So you have like a 2-hour, rotary dial timer. You spin it, it runs the snowmelt for 2 hours, and then shuts off. The better way to do it is to have an automatic control system. We typically use these on almost all the systems that we do, and it typically involves sensing 2 temperatures, or actually 2 things outside. 1 is the outdoor air temperature, and 2 is a moisture sensor to see if we have anything outside at all. Sometimes we have these all in one box. ETI makes a nice little one that you stick out in your lawn like on a residential application, and it's got a little electric grid on top of it, and if snow falls in the electric grid, the wetness of the snow completes the electric grid's connection, So it knows that it has moisture and thereby allows the system to be enabled, but it also has to be below a certain temperature. So it's got to be below, say, 39 degrees outside, and I got to detect moisture, then I'm going to turn the snow melt on. If it's above 39 and I detect moisture, I'm just going to assume that it's rain or that it's snow that's going to melt off very quickly because it's so warm outside. If it's below 39 or 37, whatever number you pick, then I know that it has the potential for freezing on your driveway or your sidewalk, so I'm going to go ahead and run the system. All right, so here's some examples here. Here's a residential system. This one is for 1,000 square foot of melting, class 1 driveway, which means we're sizing it to handle pretty much 97-98% of the snowfall hours of the year. If you looked at Bill's cheat sheets, we needed about 125 BTUs per hour per square foot. So that's where that number is coming from here. So this is basically boiling down to needing 150,000 BTUs of boiler output, which means I'm going to be buying a 160 or 180 degree input boiler. Saying here, if we have an average of 10 snowfalls a year and it snows for 8 hours per year, that's 80 hours of snow melting operation that I'd be paying to basically heat this driveway at those hours. If I decided to do that with the basic electronic control, this gives you just an idea of my pickup load and my melting load. My pickup load is basically to get this whole giant slab of concrete up to the temperature that I need it to be at. So that corresponds to a certain number of BTUs per year. In this case, 3.5 million. That's per year, right? So you're not running a 3.5 million BTU boiler. That's 3.5 million BTUs per year, not per hour. Then I got the load of actually melting the snow, right? So that's 150,000 BTUs per hour based on that layout that we had a minute ago, times 8 hours per incident. That's 1.2 million BTUs per event, times 10 events. So that's 12 million BTUs. So altogether, it's 16 million BTUs per year to run the snowmelt system with that type of control. So that's the 15 million there. And at your typical utility rate, so in this case, with natural gas, at this point in time, we made the slide with $1 a therm. You're probably better off using 80 cents a therm nowadays, but it does go up and down. But it's basically costing you $165 a year. If the fuel rate was less, maybe it cost you 100. If it's more, it costs you 200. It does not cost a lot to do one of these class 1 snowmelt systems residentially to actually operate it. And if you're buying a boiler anyway, for your space heating needs, you don't need to upsize the boiler. So really the first cost is putting the tubing in the ground, buying an extra pump, buying an extra heat exchanger. That's really your first cost stuff there. Your operating cost is 100 to 200 bucks a year for, what was this one? This was for per 1,000 square feet, right? So that was that example there. All right, so Plan B example is to put an automatic system in. This particular automatic system is one of the ones they're showing in the picture here where you put the slab in the actual concrete. We typically call that the hockey puck center because it looks like a hockey puck, obviously. So you got the concrete going around that, and this guy will detect if I need to run the snowmelt system based on snow accumulation there, temperature, and moisture. So once again, 10 snowfall events a year. In this case, though, we're going to idle the slab at 28 degrees. So we're going to try to keep this slab fairly warm so we have less pickup time than if we just let it be the outdoor air temperature. But it's pretty easy to keep it at 28 degrees because we have very few hours in Illinois anyway where we're under 30 degrees to begin with. It happens, obviously. It happens frequently, but it's not for a lot of hours. We need to get up to 38 degrees of the slab temperature to actually melt this snow, which is going to mean we're going to have to send, 80, 90, 100 degree water out there. Once again, it's 80 hours of operation in this scenario. But because we have that idle slab, it's a little bit more energy use. So showing you there the 1,500 hours of potential operation. So we skip along to the money part because we're running out of time over here. So there's my pickup loads. There's my idling load, which is obviously much larger. My total melting load. So the whole thing in this scenario, if I do that, my pickup load is 1.7. My idling load is 75,000 BTUs per year. That's where most of my energy is coming from to keep that thing idling, which means I can melt the snow faster once it happens. And then my actual melting load is fairly small. But this is costing me about $1,000 a year at $1 a therm to run that kind of system. So it helps melt the snow faster by keeping the slab slightly warm all winter long, keeping it idly warm, if you will. So it does cost a little bit more to do it that way. And then idle option C would be to keep this thing always on, which is what we would do for an emergency room or helicopter pad or something like that. So we won't go through the whole bust down of that, but obviously for keeping it always warm all the time, it's going to cost more to run, and ends up being about $1,200. So that just gives you kind of an example. We typically use this scenario when we're talking about like the emergency type facilities, class 3 applications we mentioned a minute ago. We typically use the idling scenario when we're doing regular commercial facilities, like a retail place or something like that, or a parking ramp. And then we typically use the no idle mode for residential facilities, so it only costs you $100, $200 a year to run that. All right, so let's just show you some pictures of that. Because we're running out of time, we'll just kind of flash through those and mention the last couple things. We do also use PEX for other applications. We use it for heat transfer piping. So if I got to have a line between an outdoor chiller and an indoor building, I might get this PEX, pre-insulated PEX, and buried underground. It's fairly easy to run. It comes in large rolls. So we do that quite frequently around here. Here's an article you can look at from 4 years ago now in the ASHRAE Journal on radiant cooling systems. If you're laying out a radiant cooling system, let us know. We got a guy over at REHAU that designs quite a few of these, and he can help us lay these things out, or help you lay these things out if you're designing one. We do have one in operation here locally that Alara engineers did at the Loyola Commons building. So it's Loyola University. It's right on the lakefront. You probably have seen the building before. It's basically a library and student studies type center, and it's mostly a glass building, and they're doing that with radiant cooling and heating with PEX tubing, with REHAU PEX tubing. All right, let me check real quick if there's any last questions, and then I'll cut you guys loose because I know that I talked over my time here. All right, we do have a question from Ali. Let me see here. You mentioned that chill water temperature should be above space dew point. I'm assuming we're talking about a radiant cooling system again. It can be a little less than the space dew point as far as the surface temperature of the floor is above dew point. Is that correct? I guess, Ali, in principle, that would be correct. But considering the accuracy of all these sensing devices, both the space temperature, the water temperature sensor, and the dew point temperature sensor, each one of them being plus or minus a half a degree or something like that, if you combine that with just the general fear of me, you, the controls contractor, and the building owner getting these numbers too close together and accidentally missing, it's typically why we end up setting the chill water temperature to always be 2 degrees above the dew point, the indoor space dew point. And in reality, in application, that very seldom happens because as long as the air handler is running and doing his latent dehumidification job, it's not going to be an issue. This is really a safety type sensor. So we don't need to ram it down as close as we can to the actual theoretical limit and risk that, because it should only happen when something else has gone terribly wrong, like the air handler has failed or someone's propped open a door. But we tend to, as a rule of thumb, keep the chilled water temperature 2 degrees above the indoor space dew point. All right, I don't see any other questions right now. Like I said, this is recorded, so if you want to go back and watch it, you can. It'll be posted at the same web link that you guys came to today to watch it. I'll get it posted here this afternoon or evening. You'll also be able to find it on our website, which is tucmungo.com. And then just as a reminder, in case you guys missed it at the beginning, there is a REHAU seminar on radiant heating and snowmelt systems this week, Wednesday, Thursday, Friday in Willowbrook. You can find it on the REHAU website, or if you want, send me an email and I'll send you the direct link to register for that particular course. And with that, I thank you guys for your time, and we'll see you next week. Thank you.